Today we're doing problem 79, word search. So this is another blind 75 problem that I think is pretty good to know. It's pretty interesting, it's a fun problem, so let's just get right into it. So given an m by n grid of characters, board in a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. So that's pretty important for later. And the same letter cell may not be used more than once. So let's look at the example here. So in this board, it's nice that they highlight it here. The word that you're searching for is A, B, C, C, E, D. So we can see that it exists here. On the next board, the word is C, which exists down here in the bottom right corner. The last one, A, B, C, B. We see an A, B, C, but there's no B anywhere with its neighbors. So the output is false. So really you're just trying to see if the word exists in this m by n matrix, right? And let's keep in mind that they're going to be horizontal or vertically neighboring. So the approach that we're going to take for this problem is kind of like a brute force approach, where let's just keep it simple. What we're going to do is we're going to loop through this matrix, and we're going to call on a DFS every time that we see the letter that is the first word that we want to search for. Sorry, the first letter that we want to search for. In this case, we start at the top left corner. It's an A. What's the first letter of the word we're searching for? It's an A. So we just call on a DFS from here. And we call on its neighbors, right? We check down its neighbors. And let's kind of draw this out. So if we begin here at this A, how many different ways can you go? You can go up, you can go left, you can go down, and you can go right. So 4 different ways, right? 4 different ways to search. But the way this is going to go is we're going to maintain a count. So the word is A, B, C, C, E, D. 1, 2, 3, 4, 5, 6. There's going to be 6 letters in our word, right? And the approach that we're going to take is we're going to call on a DFS and check all the neighbors from here. But we're going to increment count. We're going to keep this count. So count is actually going to start at 0. So when you call on DFS, what's going to happen is one of the parameters that we're going to pass in is the count. You pass in the word, but the count dictates what letter you're searching for next, right? So if we have A, B, C, C, E, D, and we imagine that this is some array, this word at index 0 is A. And if we can successfully, well, not even successfully, when we call on DFS on its neighbors, we're going to increment count. So it's going to be 1 next, because now we're not searching for the word at index 0, we're searching for the word at index 1, the letter, right, which is B. So we're going to come down here. And then we're going to do the same thing, check its neighbors, up, down, left, right. But what are we searching for? Well, we're searching for what's at word at index of count, which is 2, which is C. So we're going to go this way. And then we're going to increment again. All right, I'm going to fill the rest of these guys in. So C is going to come down here. We're going to increment again. We're going to check here. This is going to be E. We've hit E. Increments again, we're going to hit D, and eventually this is going to increment one more time. Why? Because we're also going to check its neighbors here. The base case is going to hit, and what is the base case going to do? It's going to check if count is equivalent to the length of the word. Well, that's true because 6 is equal to 6, right? 1, 2, 3, 4, 5, 6. There's 6 letters in our word. Count has hit 6. So that's when you know that you found every letter in the word, and it exists. If that's a little confusing, let's go in the code, and I think it'll make a lot more sense. first thing we're going to do is we're going to make the skeleton or the frame of this function that's going to call on our helper function, right? So as always, we're going to check if our input is null or if it's valid. That's good practice, I think. Just return. And we're going to set rows and columns equal to the length of the board. This is just for organization and readability. Now we're going to loop through the matrix. And call on our helper function, right? So our helper function is going to be called DFS. And we're going to pass the board. We're going to pass the position, which is I and j. We're going to pass the count, but count is the parameter. The argument we're going to pass for count is 0 because we're going to start at the 0th index of our word. That's where the word starts, where it begins. And we're also going to pass in the word itself, right? We need that. So if this is ever true, we're going to return true, which will break out of our loop. And if we ever make it out, we'll return false. Pretty simple, pretty straightforward. So just like when we're dealing with any problem that might need a recursive call, I think it's a good practice, and this is just what I have seen online and working with other people. This works for me. Make the frame, write the recursive call, and then write the recursive call itself afterwards, or the recursive function, the helper function, right? So let's write the helper function here. It's going to be DFS. The parameter is going to be the board, the position, the count, and the word, right? So first thing we should do is acknowledge and address the base cases. A happy case is if count is equivalent to the length of the word. What does that mean? That means that we have successfully traveled down the word search path and found all the corresponding letters that are in the word. So we can return true here. And then we can check for index out of bounds. If I is less than 0 or I is greater than or equal to the length of the board. Similarly with j. And what do these mean exactly? Remember how every time we call in a recursive function, we're going to check on its neighbors. That's how DFS works. When you check on your neighbors though, there are bounds to our matrix. So if I ever gets too large or we decrement it too much, similarly with j, we're gonna fall out of our matrix. So you wanna make sure that you're checking for this. If you don't, then you get the index out of bounds error, and then you're sad, and then you cry. The last check that you want to do is you want to make sure that you're not even wasting your time. So what do I mean by that? If word at count is not equal board at ij, what does that mean? If we're at a cell where the contents are not even the same as the letter we're searching for, the next letter in the word, we're looking down the wrong path. So don't waste your time, right? So return false. Now, just like with DFS, you want to make sure that you're marking the places that you've been to before. So that's what this is doing. Temp is going to be equal to the board at ij. And we need to store the contents of the cell because later on we have to add it back in when we're done searching its neighbors. We don't want to influence any future searches with incorrect data. So that's what temp is doing here. We're just storing the cell value because now we're going to check the neighbors. We're going to set that value in found. Found is just going to be equal to the recursive call. DFS on the board, I plus 1, j, because we're checking the neighbor, right? So I plus 1, j, count plus 1, and now the word. And we're going to duplicate this several times. So we've done I plus 1. Now now we want to do I minus 1. And we're done with the i's, right? So now we want to do the j's. J plus 1. And finally, j minus 1. This is checking its neighbors, right? We don't need this last or. So now that found is in there, we can now set the board at I, j equal to 10. We'll add that cell value back in. And before that, I almost forgot. The whole point of this temp is because we're going to wipe the board value so that we're not messing around during this recursive call in the search. If you have duplicate letters and you end up at a cell that's letter A, you remove A. If you don't remove A and you want to search for A in the next recursive call and you check the neighbor, you're going to look back at yourself and then you're going to keep going back and forth. So that's what this prevents, right? So we're going to set this to nothing. And then at the end, we can return found. So let's take a step back. Let's look at this code. And let's try to run it. Hopefully this works. It doesn't work. So the problem is this is actually supposed to be board at index I. If you're checking index out of bounds for j's, that's for the columns. So we've already checked length at board for I. We've got to check length of board at index I. Pretty sure that's what's causing this problem. Great. Let's submit this. Awesome. Yeah, okay, so this works. Runtime of this algorithm, it's pretty not good. It's kind of bad, actually. It works, but it's not great because the problem is we're running a DFS on potentially every single cell in our matrix in the worst case, right? We're looping through this matrix, and that's what's happening down here in this loop, this double for loop through the n by n matrix. And every single time that we found a letter or cell that we want to run DFS on, we're actually going to keep up 4 different calls. So I think it's going to be, I think the runtime actually ends up being something like big O of m plus n. M plus n is the runtime of DFS, and it's going to actually be 4. And the reason it's 4 is, like I said earlier, because there's 4 separate calls. Whenever we call on DFS on your neighbors of a cell, there's 4 different neighbors, right? Because it's adjacent horizontally and vertically. So 4 to the what power, it's actually going to be n, where n is the, or let's say k, 4 to the k, because this is as deep as we can go. The reason I'm saying that is k is going to be equivalent to the length of the word that gets passed in here as the parameter that we're searching for. So the word that we're searching for is the max depth that we can reach. So that's why I think the runtime is big O of this m plus n times 4 to the k, where k is the length of the word itself. So it's not great. It's actually quite slow. This is kind of a nightmare, but it's a brute force solution, right? In a way, and it's you're checking your neighbors, so you can't help that you're gonna have this 4 to the k thing. But yeah, I hope that helps.